right, so we are live now. And hey, everyone, thank you so much for joining today's session. Um, we're going to give a couple more minutes just for people to join in and take it from there. Let us know where you're joining from today. I'm joining in from Toronto, Canada this morning. It's a sunny day here in Toronto in the winter, so that's great. All right, just a moment. We'll give a couple more minutes. All right, I see a few people joining in. All right. Let us know where you're joining in from today for this session, and we'll be starting in one more minute. We'll just give one more minute to go.
Okay.
All right, I think we can get started now. Thank you so much, everyone, for joining this session. Today we have yet another interesting talk where we're going to learn about Apache Doris, a modern data warehouse for real-time analytics, and how you can use Doris as a compute engine on top of Apache Hudi, for your kind of fast federated queries on data lakes. Um, so yeah, let's quickly do a round of intro. My name is Dipankar. I'm currently a staff developer advocate here at OneHouse.ai. I contribute to Apache Hudi, and I'm also part of the Xtable project. And yeah, it's great to be here. And we have Mingyu Chen, who is a PMC chair at Apache Doris, who is going to present today about what Doris is and the integration between Doris and Hudi. Mingyu, just a quick introduction to you. Yeah.
Okay. Thanks so much for the invitation from the Hudi community. My name is Mingyu Chen, and I am the PMC chair of the Apache Doris. Yeah, very nice to meet you.
All right. Thank you so much, Mingyu. So, what we'll do is, in terms of the agenda, I'll warm up things from a Hudi perspective. I'll go through pretty much like an introduction to Hudi, and then we will look at how things started at Uber back when Hudi originated and how it kind of enables a lakehouse architecture. Then Mingyu will take away the rest of the session with everything around Apache Doris and how like Doris Hudi integration helps people do analytics on top of data lakes. All right. So let's take a step back to understand how Hudi started, right? Because the problems that we're seeing at Uber back then, when Uber was in a hyper growth mode, they were moving from kind of a data warehouse environment to a data lake, right? And the problem was whether you had like a cloud object storage or on-premise Hadoop file system, it is an immutable storage system, right? So you had to put a database or a transaction layer on top of the data lake to work with it. And that's basically how Hudi originated. So the problem that Uber ran into specifically was with their trips database, right? So like everyone else at the time, they were doing kind of bulk uploads, right? So this process would take them like 120 terabytes of data every 8 hours to convert from like the old format to Parquet. And then they would do a full recompute of all the downstream tables again, right? And that means the end-to-end data freshness would be around 24 hours, which is bad. So they noticed their ingest performance was really bad with a lot of unnecessary reading, writing, and compute span without any guarantees that a job would finish successfully, right? Plus, there were no concurrency control, atomicity guarantees, rollback, and those kind of things. So this was the basis of how Hudi started, and as you can imagine, these are much complex problem to solve than just purely table format. Hudi actually started with a whole range of database kind of problem because we are talking about the transactional layer thing. It's pretty similar to how a database works. So things like updates, incremental processing, and deletes, and those kind of things. So when Uber started to tackle this problem, they realized they weren't facing a completely new problem, right? Pretty much all of the database system dealt with this kind of challenges. It is just that they needed to figure out a way to implement these in a way that could fit in a data lake and architecture, right? So essentially what they decided was if they could build a system that could be capable of handling updates, delete, upserts, so they can absorb the changes faster into the table and then process the changes faster, right? So that was super important. And while we're able to do things like faster updates, can we query a snapshot consistently, right? So no dirty data, and it sees things are either committed atomically or not. Plus the ability to look at things at specific point in time. So if there is a mistake, you can basically time travel, to back to a time when there was a things were right, and basically hit rewind from there. Also, this wasn't just the ingestion problem, right? There was also the need to kind of incrementalize the downstream ETL. So, for instance, can we consume only the changes, right, instead of doing the full recompute? That was very expensive, right? And that led them to build the incremental changes, which is very core to Hudi, and also separates us from other open table formats out there. So all these principles guided the core primitives of Hudi, like things like upserts, incremental processing, snapshot isolation, and this kind of things. So when Hudi started at that point, it was referred to as a transactional data lake. Today we have terms such as lakehouse, but of course the idea was pretty much the same. So you could, start with your cloud object storage where your data files like Parquet was sitting, for example. Then you throw in a bit of metadata on top of the Parquet data files and a transaction log on top of that. That way you're able to expose the API, which can then be utilized by, Spark readers or writers or any kind of compute engine for that matter. Uh, so Hudi introduced two kind of storage type, which is like the table types in Hudi, which is copy on write and merge on read. And these ideas are actually heavily borrowed outside of Hudi and other table formats now as well. And we'll understand a bit more on these table types in a few minutes. So once Hudi had all these kind of capabilities, right, the resulting architecture was basically like a database abstraction for cloud object storage, right? Specifically by decoupling storage and compute. So now we could have things like faster upserts, different type of indexing schemes were actually built in Hudi, which is very unique to other table formats as well, right? And you can incrementally build ingest table. So incremental processing is a concept actually pioneered from this. For example, we talked about the problem with Uber, right? So instead of ingesting 120 terabytes of data every 8 hours, what it could do is it could just upsert a few gigabytes of data every 10 minutes, right? And this really makes for efficient downstream ETLs. So Uber actually builds most of the core warehousing tables in an incremental fashion, where they actually process only the incremental changes every few minutes and then run it. This is not as ubiquitous as we would want it to be today, but we focus a lot on this aspect with Hudi today. Okay, so moving on, we have come a long way from this kind of beginnings, thanks to the diverse community contributions, that kind of makes Hudi the foundation for a lakehouse architecture today. So what's a lakehouse, right? As you might have guessed from the name, it's a combination of a data lake and a warehouse. But of course, this is not just a mere combination of the two. So the whole idea is basically to take the best of the both worlds. So for instance, data warehouses have great data management optimization capabilities and things like, compaction, clustering, metadata tables, and the ability to do things like time travel, schema evolution for the matter, ability to do all those things with ACID guarantees, right? That is super important because that was one of the main challenge with the data lake environment, right? Similarly, with the data lake, it gets the scalability part of it, right? Because now with the cloud object storage as well, like S3 or Azure Blob or Google Cloud Storage, cost-wise, these object stores are kind of comparatively very cheap, which is really great for organizations and users to really drop in any kind of data, structured, unstructured, and you can take it from there. So a lakehouse basically builds on that idea, and the core of the core ingredient of a lakehouse is basically the table format. So Hudi enables kind of an open table format, but it's also important to note, and we touched upon this a bit, that Hudi is much more than a generic table format, right? With the integration of various table services, we talked about like clustering, compaction, and there are platform services as well. For example, things like how to efficiently do ingestion. Hudi has something called Hudi Streamer. Then there are various data quality initiatives within Hudi. So these kind of platform services and table services, along with the table format, really kind of sets the foundation for a lakehouse platform. So as you can see in this image here, there are various components involved in a lakehouse architecture. I'm not going to walk through every single thing, but if you see in the bottom part, we have the lake storage. This is where the data is coming to land from any kind of system, whether it's a operational system, transactional system, or any kind of streaming system. And then you have the file format on top of that, right? Which is basically your Parquet file or org file, whatever file it is. And then on top of that, basically where it's kind of Hudi's transactional database layer comes into the picture, right? So this includes all kind of things like table services, like indexes, concurrency control, among so many other things. So Collectively, these services offer significant enhancement to data and table management, which is super important for like lakehouse architecture or data lake architecture. And of course, we have other things like catalogs and the various BI tools, ML engines to process your data from there. So now let's quickly delve into some of the specifics of Hudi, by going over the Hudi table format and try to understand how Hudi lay out the files in the, in a distributed file system, right? So two important concepts to take away from here. One is the file slice, and other is the file group. Okay. So a file slice basically consists of a base columnar file, which is mostly Parquet file, and that is a file that is produced at a certain point of time, right? On top of that, the file slice also contains a set of log file, that basically has all the updates to the base file, all the updates that has happened to the base file from a particular point of time that was committed. But one thing important to remember here is that the log file is specific to only a set of table called merge on read and not copy on write. And we're going to talk a bit more about that. So when we have group of such file slices, we call them as file group together. And when a writer comes in, the records are written to the file slices, and each record has a key that is mapped to a particular file group. Okay, and this assignment will never change, and that's kind of the basis for things like faster and incremental updates, upserts, and those kind of things. Quickly, just to end this particular slide, we have two important things here. One is the timeline, of course, and the other is the metadata table. So when a record gets written into a file group, Hudi's timeline is going to record what commit action was done in that particular timeline. So the timeline is basically like an event log, if you may, and it keep tracks of all that has happened within that table. And then there is the metadata table, which is actually a Hudi MOR table, merge on read table. We'll cover a bit more about that, but at a high level, it stores information like file level statistic, partition information, indexes, and those kind of things. So now let's quickly touch upon the two different table types in Hudi. The first is a copy on write. Basically, in a copy on write table, the file slices will contain only the base columnar file and not the log file. Okay. So every time you commit new data, Hudi makes a copy and produces a new version of that base file. Okay. So as you can see, there are different color coded version here at different commit time. Let's say you insert a record A, B, C, D, E at commit time 0, and Hudi organizes them into 3 files, right? So when you say like you in the next commit, when you change A to A prime and D to D prime, you see that the blue color record has been written to orange colors now because Hudi basically rewrote that file with the new record. Okay, and it makes a copy of that. So now if kind of Hudi provides different query types to query the data, of course, like for example, there is snapshot query, which allows us to query a particular like the latest snapshot of time. And there is incremental query, which we talked a bit about incremental processing, which is only about getting the latest states and changes to the table. So if we do an incremental query at this point of time for commit time 1, we will see that we are only getting A prime and D prime because that's the only thing that we change in this particular state from the last state. And if we do a snapshot query, we'll get basically the latest state of the table, which is A prime, B, C, D prime, and E. Okay. So one thing that you might have figured out here is that copy on write has a much higher write amplification because you are making copy every time you write. Whereas on the read side, the amplification is 0, which is very important for analytical workloads. So the last part is the merge on read table, which is actually more flexible. There are more operational things to be done on the background, but the idea is the same. Okay. So if we update A to A prime here in this particular case, we don't rewrite the entire Parquet file. So what we do here is we just basically store the incoming update to a latest log file, which in this case you can see in this particular log file. And eventually by applying a kind of a compaction process, Hudi will merge the base file with the log file to produce a new version of the base file. Okay. So as you can see, the overhead of kind of merging is towards the read, whereas we are doing less on the write side. So the write amplification is great here, right? So again, there are different query types here. In fact, like there is something called read optimized query in an MOR table, which is basically allows you to like balance query performance over freshness of data. So with the read optimized query here, you are going to like not merge basically the base file and the log file and only give the base file record. So similarly here, if you go to like commit time 0, you can see all the the first commit states and the records. And if you go to commit time 1, you can find the snapshot query will give the A prime, B, C, D prime, E. Incremental query will give the A prime and D prime, whereas the read optimized query will give me only the records from the base files, right, that have not been merged yet. Okay. So that is pretty much it in terms of the concepts. So some resources for here to join the community Slack, where we have a lot of engaging discussions. The community is really booming, and if you want to contribute or be updated and apply Hudi on your work, join us on our socials as well. That's where we post our latest updates happening in the Hudi world. So that's about Hudi. Now I'll hand over quickly to Mingyu, who will take you over about Doris and kind of Hudi Doris integration. All
Okay,
right,
thank
Mingyu,
you.
over to you. I'll pull up your slides then.
Okay, I will stop and
Sure.
okay, share my. Wait for a moment. Okay, can you see my
All right.
screen?
Yes. All right. I think
Okay,
you're good to like
okay.
the yeah. Cool.
Okay, so let's get started. First of all, I would like to explain what the Apache Doris is. Doris is a modern data warehouse for real-time analytics. It delivers lightning-fast analytics on real-time data at scale. This is a picture from the official website of Apache Doris. You can see the position of Doris under a big data architecture. It is a relative downstream component. The upstream system include relational database, data streams such as Kafka and Pasa, and a data lake system and other structured or semi-structured data. And Doris can access this data in two ways. One way is to read and import the data into Doris through various data pipeline, data processing systems such as Flink, Spark, or some Doris built-in important functions, and manage it as Doris internal table data. The other way is to query this data directly through the connector framework. It can save time on data import and conversion, especially for query acceleration on top of the data lake. So Doris can directly provide query service to end user, including the reports, the ad hoc analysis, and the ETL data processing, etc. And I will talk about them later. Okay. This picture is an overall architecture of Apache Doris. You can see that it is a typically share nothing MPP data warehouse. From the usage perspective, Doris has the following features. First, the Doris structure is very simple. Doris has only two types of process, the front end and the back end. The front end is mainly responsible for user access, the metadata management, and the querying plan. The backend is mainly responsible for data execution and the storage. Both modules can be scaled out. In addition, Doris does not rely on any other third-party components. The second point is that it is very easy to use. Doris supports the MySQL compatible protocol layer, so you can use any standard MySQL client to connect to Doris, and then query the data using standard SQL language. The bottom picture, the picture at the bottom show the basic use of Doris, like a create table statement and a SQL query. So the third point is the high performance, including the full vectorized execution engine, the column storage, and the secondary index, the cost-based optimizer, etc. So we will further upgrade the Doris to the shared data architecture in the version 3. It will be released in the Q2 this year. So you will see a new Doris in storage and computation separation architecture. So this is an architecture of Doris. Okay, this picture shows the four main application scenario of Doris. The first is the real-time reports and the data analysis, including the high concurrency and the low latency real-time reports, such as querying the build data, the delivery data, etc., as well as the high throughput ad hoc analysis queries. Doris help user to provide an excellent query performance in these scenarios through various techniques such as the vectorization, the materialized view, spill to disk, and point query optimization. Okay, the second is the user profiling and the behavior analysis. User profiling analysis can help enterprise better promote and improve their service and products. Doris use the bitmap and other bitmap storage capabilities to help user quickly perform user profiling and analysis, such as generating a group of users to determine who should we deliver our advertisement to. Okay, the third is the log management and analysis. Many companies have a large amount of log data, including the system operation logs, the business logs, etc. Doris can provide users with the high performance log data import and the low-cost data storage capabilities. It also provides user with the high performance log data analysis capabilities through inverted index, the full text index, and the variant column type, etc. So the last one is the data lake analysis. Through the Doris connector framework, Doris can directly query and accelerate data on the lake and or other external data source without importing their data to Doris. This is also the focus of today's sharing, and I will introduce the technical details of this part later. So the above is the brief summary of the Apache Doris, including the architecture, the application scenario, etc. I hope it can help everyone to quickly understand what Apache Doris is. Okay, let's briefly introduce the Doris community. Doris is a very active community with an average of more than 100 active developers per month. It can also be seen from the number of commits of each version. In the Doris version 1.2, it includes 2,400 commits, and in the Doris version 2.1, it includes more than 5,000 commits. Compared with the year 2022, the trend in some community indicators of Doris in 2023 can also reflect the activities of the community, such as the stars, the folks, the commits, and the issues. Oh, the Doris has trusted by many enterprises all over the world, and I'm very excited to see the rapid development of Doris. And I'm also very happy to communicate and learn from the other great communities like Apache Hudi. Okay, so let's move on to the second part to introduce how we bring data lake to the Doris. Let's first look at the Doris connector framework and the problem it hopes to solve. The frame can be divided into 3 layers. The bottom layer is called the data layer, including the data storage such as the HDFS, the cloud object storage, etc., and the data format storage above them, including Hudi. And the other part is the various database system that can be connected through the JDBC. The second layer is called the data processing layer. In this layer, one way is that user can access the data in the data layer through various connectors officially provided by Doris, such as the Flink and Spark connector. And after processing, the data is stored in Doris storage. Okay, the other way is you can directly access the data in the data layer through Doris connector SPI for query and analysis. Okay, the top layer is called the query layer. In this layer, user can leverage the Doris lightning fast query engine to query the data in both Doris internal storage or external data source. Therefore, the problem that the entire architecture wants to solve includes 3 points. The first is the data lake query acceleration. That is to directly query the external data source with high performance. The second is the unified data analysis gateway. It can help user perform join query on various heterogeneous data source through standard SQL language. And the last is the unified data integration. Through a unified access mode, user can perform unified data processing through Doris. Next, I will introduce the technical details of Doris in data lake query acceleration from four aspects. They are the metadata catching, the data catching, the native open format file reader, and the I/O optimization. Okay, the first is the metadata catch. In order to ensure the efficiency access to metadata, Doris will catch the metadata from external data source. The catched object include information such as the database, the table, the schema, the partition, and file list. At the same time, in order to ensure the freshness of the metadata, Doris also provide a variety of metadata synchronization mechanism, including the manual or automatic refresh of the metadata or setting the TDL. And for the Hive Meta Store, Doris also supports subscribing the Hive Meta Store events, which can achieve the near real-time synchronization of the metadata. So even you need to access thousands of files metadata with the cache, it can be processed within the milliseconds. Okay. The second is the data caching. The main issue here is to accelerate queries for the hot data. Doris generally greatly improve the query performance of hot data or the frequently accessed data by catching the fire blocks on local high-speed disk. At the same time, the consistent hashing is also used to determine the distribution of the cache. When the node is elastically scaling in or out, it will try to avoid the cache missing and improve the cache hit rate. In addition to the fire catch, Doris also provide other types of general catching mechanism. For example, the query result catch, query result catching can directly catch query result for the same SQL query. The partition catching can catch the query result according to the partition level. In this way, when querying multiple partitions, the catched result of some partitions can be merged with the result of the real-time queried partitions, thereby reducing amount of data that need to be calculated in real time during the query and improve the query efficiency. Okay, the third point is the native support for open file formats. Here we mainly focus on Spark+Hudi and ORC format. Our native file readers not only provide a fully vectorized reading processing, but also fully utilize the characteristic of the file format. For example, the intelligent index such as the columns, the min max value, statistics, dictionary encoding, and the Bloom filter, etc. It can help skipping irrelevant Spark+Hudi row group or the ORC stripe or the data pages. At the same time, we also support the lazy materialization in native reader. This method can significantly reduce the amount of data that needs to be read from the remote storage system and improve the query efficiency when there are filter conditions in the query request. Okay. The last point is the I/O optimization. One of the biggest difference between the data lake query and the internal table query is that the data is read from the remote storage. So both the I/O latency and the throughput are far inferior to the local disk. Therefore, the I/O optimization is the main focus in this scenario. In Doris, we use the I/O merge strategy to reduce the number of remote I/O and improve the I/O efficiency. For example, in this figure, in the original situation, there are 8 I/Os and need to be performed. But after merging, only 5 I/Os need to be performed. Although there is a read amplify problem, you can see after merging, it read 3 more megabytes. But compared with the performance improvement brought by the reduction in I/O times, the additional read amplification is acceptable. In addition, Doris is optimized for small files. For example, when the file is less than 1 megabyte, the entire file will be directly read and loaded into the Doris memory, therefore improving the query efficiency in a large number of small file scenarios. Today I briefly introduced the optimization of Doris in the data lake query acceleration scenario from 4 respectively the metadata caching, the data caching, the open file format reading, and I/O optimization. This graph is a comparison of the query time of Doris and the Trino version 435 in the TBCH 1 terabytes benchmark with the Spark+Hudi format. It can be seen that in the case of remote read, which means without cache, Doris can reduce the query time by 40% compared to Trino. When the cache is enabled and completely hit the cache, Doris can further double the query performance. Okay, in the last part, I will focus on Doris' ability to support Apache Hudi. Here is a brief introduction to how Doris supports Hudi data query. Compared with the Hive, Hudi support flexible update and delete operation on data. So In addition to the Parquet file, Hudi also has log file for recording the updated or deleted data. Therefore, the read access from Doris to Hudi is divided into two ways. One is for copy on write table or the read optimized table. Doris can directly read the Parquet files through native reader to obtain the best query efficiency. And the second way is for the merge on read table. It will it will also be divided into two parts. For the file split without the log file, the base Parquet file will be read directly through the native reader. And for the part with log files, we leverage the Spark API through the GNI framework to perform merge on read operation. So all in all, Doris will try to speed up data access by using native readers as much as possible. Okay. Next, I will use Spark and Hudi and Doris to make a brief showcase in about 7 minutes. I have recorded the video so that it can be save us time to show. Okay, wait for a moment. Okay, can you see my screen?
Yeah,
okay, let's get started.
Yeah. All right.
Okay, here we have prepared a very simple Hudi environment because Doris currently does not support writing Hudi data directly. So here we use Spark to generate a set of Hudi tables. We use the line item from the TPCH benchmark. The scale factor is 10 for both copy on write table and merge on read table. First, let's take a look at the Spark. So we use the Hudi database and show tables. We can see the Hudi tables. Now we can see the commit history of the table. First is copy on write table. Okay, you can see that the table has imported about 60 million rows. Afterwards, we perform two insert operations. Each operation includes 10 rows. However, the number of inserted rows counted here seems to have some problem. We have not yet figured it out, the specific reasons, but it does not affect the correctness of the data itself. Next is the merge on read table, which also imported about 60 million rows. After doing several insert and update operation, a merge was triggered. After the merge, two update operation was performed. Then let's take a look at the Doris. This is a single node environment of Doris on a single node with 24 cores and 96 gigabytes memory. Okay, you can see that this is a single node. Sorry, it's a single node Doris. Okay, we have created a Hudi catalog. You can see that the metadata is stored in the Hive metastore and the data is on HDFS. Next, we switch to the database under Hudi catalog, and we can see the same table. Okay, let's see the creation statement of the table. For example, the copyright table. Yeah, we can see that this is the Hudi format table generated by Spark. Okay, next we use query 1 in the TPCH benchmark in both Spark and the Doris. Here we first query the copy on write table. Okay, this is in Spark, and we can also query it in Doris. Okay, just wait for a moment. Okay, you can see that the same result can be obtained on both sides. However, the query time of Doris is significantly faster than Spark. But I am not the expert on Spark. Maybe Spark needs some additional parameters for tuning. Okay, we can use the explain statement to see Doris execution plan. Let's give a try. So explain the SQL. Okay, You can see that this table has 200 files, and because it is a copyright table, so all files can be read through native reader directly, so the query speed is relatively fast. Then we are using Doris to query the merge on read table. Okay, we can also use the explain statement to see the query plan. Okay, you can see that most of the shards of this table can be accessed directly through the native reader, and some incremental data will be read through the GNI for merge on read operation. So the execution time is also relatively fast. Okay, next, let's look at how Doris can query the updated data in Hudi immediately. Here we first query the original data on Doris. Okay, you can see the line number value is 4, and then we update this data in Spark. Yeah, we update the line number to 5. Just wait a moment. Okay, then we query the data in Doris again. So you can see the data is updated. Okay, next we will demonstrate the time travel feature of Doris on Hudi. Let's take a look at the committee story first. Okay, we can query data before update through the time travel. So let's use this timestamp. You can see the line item. The line number value is 2, and let's change the timestamp to this. So you can see the line number value is changed to 3. So this is the time travel of Doris on Hudi. So finally, let's take a look at Doris support for Hudi incremental read. Let's still select a time period time from the committee story and perform incremental query in Doris. Okay. Okay, that's you can see we use the begin time, this begin time and this end time, and to query this table. So you can see we can only query the incremental data within this time period. We can verify it in Spark. Okay, the same begin time and the end time. Okay. Okay, we got the same incremental data. So similar, let's look at the query plan of the incremental query. So it can be seen that for the incremental query, we will still try to use native reader to read part of data to obtain the best query speed. Okay, let me share. Okay, can you see my screen?
Yes, I do.
Oh, okay. That is all, and we are continue working on add more features about holding Doris. And finally, everyone is welcome to use and or the participate in the Doris community. Here is a various way to connect to the Doris community, including the email, the GitHub, the X, the Slack, and welcome to join. Oh, that's all.
All
Thank you.
right. Thank you so much, Mingyu Chen. Yeah, this was a really nice presentation, and specifically the demo was good to see. At least like have that kind of practical experience with like the theoretical thing that you put up there. So thank you so much for helping us understand how Hudi and like Doris works. I have a more generic question. I'll see just if we have any questions in the comments as well. Okay, so I think I'll just go ahead and ask. So Doris is another. It says a real-time data warehouse.
Yeah.
Real-time data warehouse. So how does it kind of differentiates from other like existing open source or proprietary data warehouses like today? Specifically, what I'm like curious about is why the real time in there. Is there any specific like functionalities or features that kind of make stories like really special for these kind of workloads, right?
Yeah, I think the 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 main difference about Doris and other OLAP system is that the is simple architecture. Yeah, the first is that there's simple architecture. As I said before, it has only two process, two modular, the front end and the back end, and it does not rely on other third party components. And also, it is very easy to use. You can see that we can just use it as an a MySQL to create table, to query, use the SQL standard language.
Right.
And the third is the fast. Yeah, the fast is the main the the main prongs of the Apache Doris. Everyone used it to run the TPCH or TPCDH benchmark, or use the Doris to query their real data. You can see how fast it is.
Right. All right. Thank you so much. Yeah, that was more of a personal curiosity. So yeah, just putting it out there. We have a question from Sudha. So I think this CJ is like, can you help understand the small file IO optimization, like how it does, like at a high level?
Uh, 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 um, just wait
Yeah,
a
the
moment.
question is around like small file IO optimization and how Doris does it.
You mean how do we do the small file
Yes,
optimization?
that is right. Yes.
Uh, it is relatively simple for a small file because we see some user to generate a lot of small files is less than even one kilobytes. So in this scenario, the Doris will read all the bytes, read the entire files and load it into the memory, and then to read the data just from the memory. So it will be very fast. Without list optimization, it will first to read the header or the footer of the file. That is one IO, and then read the content. That's two IO. So it may be very slow when, especially when the data is stored in the cloud storage, such as the S3.
Right. Well, that hope that has helped, like, answer the question. One last thing, are there any more integrations planned between Hoodie and Doris, like community, from like a technical standpoint and like future perspective?
Yeah, we are just like in my showcase, we are just implemented the incremental query. You see it will be released in the version, I think 2.1 2.1.1, I think. And later we will further support the hoodies the metadata table to
Okay.
query more metadata and to support more index for the file pool or the partition pool to also accelerate the query performance. Yeah.
That would be amazing to, yeah, yeah, that would be like a great use case as well, and like leveraging the metadata table for those kind of capabilities. Yeah.
Yeah.
I have one more questions here. I can put it up here. It's from Zaki. He says, can you tell us more about the TPCDS Doris versus Trino? Did you do other benchmark or test in use cases comparing Doris versus Trino?
We had just make the TPCDS and the TPCH benchmark with Doris and Trino. Yeah, and but here I didn't have the details. Maybe I can show it somewhere else. But you can see this slice. So this is the total query time of the TPCH. In the scale factor is the 1 terabytes. Yeah, so you can see the Doris is for about the 40% faster than Trino. Mm.
Right. And
So okay, yeah.
yeah, hopefully, yeah, that kind of answers the first part. Did you also run any other like benchmark or use test cases like comparing other use cases like or are there any other available resources in the Doris community to like just read more about it?
Not yet.
All
We just to run the TPCDS and TPCH
right.
just
Got it.
to benchmark. Yeah,
Got it. Yeah.
but we have tested the query performance in some of our users, and it also provides some very good performance.
Awesome. Awesome. Thank you so much. Yeah.
Okay.
I'll just give her a more moment here just to see if we can get many more questions around Hudi, Doris, and then we'll probably end the session after that. So yeah. All right. I don't see anything else, so I think that would be it for today. Thank you so much once again, Mingyu, like for joining the session today. I know it's a bit later on your side as well, but really it was really insightful talk and it was really helpful for the community, hopefully. And in case we see any more questions, we'll head it to your way. Thank you so much.
Okay, thank you so much too.
All right. Thanks everyone for joining the session, and we'll see you in the next live session. All right. Bye.
Okay, bye.